Welcome to week 5 of the NPTEL course on functional programming in Haskell. I am SP Suresh and I shall be taking over from Professor Madhavan Mukund for the next few weeks. In today's lecture, we shall be looking at user-defined data types in Haskell. The simplest way to define new data types in Haskell is the so-called enumerated data types. Here is an example: data bool equals false or true. You define the new data type using the data keyword and give the name of the type here, bool. Notice the capitalization, and then you enumerate all the values that can be part of the type. In this case, it's either false or true. Notice the capitalization again. Another example is day. You declare it by saying data day equals Sunday or Monday or Tuesday or Wednesday or Thursday or Friday or Saturday. These are all the possible values of the type day. Here is another example: data shape equals either a circle or a square or a rectangle, but a circle has a parameter, namely the radius, and a square comes with a parameter, namely the length of the side. Similarly, a rectangle also has a parameter, namely the length and breadth. This enables us to declare new data types which can take infinitely many values. You have circle 1, circle 2.0, circle 3.0, and so on. One circle object for every float value. Here are some examples: circle 5.0, square 4.0, rectangle 3.0, 4.0. This is a rectangle with breadth 3 and length 4. You can define functions on user-defined data types in the usual manner. Here are some example functions defined using pattern matching. For instance, you can define what a weekend is. Weekend is a function from day to bool, and here is the definition: weekend of Saturday is true, weekend of Sunday is true, and weekend of anything else is false. Similarly, you can define an area function, which is a function from shape to float. Area of a circle with radius r is pi r squared. Area of a square with length of side x is x squared, and area of a rectangle with length L and width W is L times W. Are there other ways to define functions on user-defined data types? Yes. For instance, here is another way to define the weekend function called weekend2. The definition is here: weekend2 of D is true if D is equal to Saturday or D is equal to Sunday, and it is equal to false otherwise. But if you enter this program as it is in GHCI, you will get an error. The error message will be something like this: no instance for EQ day arising from a use of the equality operator. Let us see how to fix this later. Here is another function you can write, which is a function from day to day. It gives the next day. For instance, next day of Sunday equals Monday, next day of Monday equals Tuesday, and so on. Next day of Saturday equals Sunday. Now, if you load this function in GHCI and invoke next day of Friday, it will again lead to an error, and it is the following error: no instance for show day arising from a use of print. We'll see what this means and how to fix this in a later slide. To check equality of two values of a data type A must be declared to belong to the type class EQ. We have seen the notion of a type class in earlier lectures, and we have also seen the type class EQ in detail. So to get weekday 2 to work, we need to add day to the type class EQ. And we add day to the type class EQ as follows: data day equals Sunday or Monday or Tuesday or Wednesday or Friday or Thursday or Saturday, deriving EQ. The keyword is deriving. When we declare day to derive from equality, the equality operator has the default behavior. Sunday equals Sunday, Tuesday is not equal to Friday, Monday equals Monday, etc. Once you declare day to be deriving from equality, then weekday 2 compiles without error. To make the next day function work, we must make day an instance of the type class called show with a capital S. We have to declare it as follows: data day equals Sunday, Monday, Tuesday, etc. deriving EQ comma show. The type class show consists of all data types that implement the function show with a small s. The function show converts its input to a string which can be printed on the screen. We need not define it explicitly for the data type day. If we do not give an explicit definition, there is a default definition that Haskell provides, which is to just give a default text representation for the data value. For instance, show WED is just the string WED. We can also derive day as an instance of the type class ORD, which is an ordinal type. When we do this, an order is defined on the data type day as follows: Sunday is less than Monday, is less than Tuesday, etc., is less than Saturday. And this order is determined by the order in which the data values are enumerated in the data type declaration. We can also derive shape to belong to various type classes. You can say data shape equals circle float or square float or rectangle float, deriving EQ, ORD, and show. Now you can use all these functions on data, on values of type shape. For instance, show circle 5.0 will just be the string that says circle 5.0. Square 4.0 is equal to square 4.0. The equality check is derived from the equality on floating point numbers as well as the name square or circle or rectangle. For instance, square 4.0 is equal to square 4.0 because both the parameters and the name here are equal. Square 4.0 is not equal to square 3.0 because even though the names are equal, the parameters are different. Circle 5.0 is not equal to rectangle 3.0, 4.0 because they are two different types of shapes. One is a circle and the other is a rectangle. And we have also derived it to belong to the type class ORD. So there is an order defined on shapes. Square 4.0 is, for instance, greater than circle 5.0 because square comes later in the declaration than circle. The names square, circle, Sunday, Monday, etc. that we have used are called constructors. They are nothing but functions. Sunday, for instance, is a function that's of type day. It's a function that accepts no input but produces an output. Rectangle is a function with two parameters. So it takes two floats as inputs and it produces a shape as output. So rectangle is a function whose type is float, arrow, shape. Similarly, circle is a function whose type is float, arrow, shape. These constructors can be used just like any other function. For instance, circle can be invoked on the input 5.0 to give a shape. You can map the circle function over a list of floats to get a list of shapes. For instance, map circle on the list 3.0 and 2.0 will give you the list consisting of circle 3.0 and circle 2.0. Here is another way of defining types. Data person equals person string int float string. Now you'll see two occurrences of the word person here, one on the left and one on the right. On the left, it denotes the name of the type. On the right, it is the name of the constructor. Now, unlike in a type like shape, where we had three constructors, circle, square, rectangle, here we have only one constructor, though we have many parameters. The convention in Haskell is that if a data type has only one constructor, then you use the same name for both the type and the constructor. So the person that appears on the right is a constructor, and the person that appears on the left is the name of the data type. So here we say that data person equals person string int float string. The intention is that the first string is the name of the person, the int here is the age of the person, the float here is, let us say, the height of the person, and the last string here is the phone number. So for instance, you might say guy equals person alpha 21 5.8 and some phone number. How do you extract the name of a person object? You write a function name whose input is person and the output is string, and the definition is this: name person n any age, any height, and any phone number equals n. Here is a function that extracts the age of a person. Age is a function from person to int, and the definition is age person anything a anything equals a. You can write a height function which says height person anything h anything is height is h, and here is a function that extracts the phone number of a person. Phone person anything p equals p. We are using pattern matching and we are using don't care patterns in all these definitions. But this kind of definition is quite cumbersome, so Haskell offers an alternative, easier syntax which is also familiar from other languages. You can define the person type as follows: data person equals person, and within braces you say name which is of type string, age which is of type int, height which is of type float, and phone which is of type string. So you are naming all the fields directly in the data definition itself. And these names here, name, age, height, phone, etc., are really nothing but the functions that we defined earlier. Name is a function from person to string. Age is a function from person to int. You declare new objects of type person in this syntax as follows: guy equals person, within braces you say name equals alpha, age equals 21, height equals 5.8, and phone equals phone number. This is an easier syntax that Haskell offers. To summarize, we've seen simple ways of defining new data types. The keyword data is used to declare new data types. The keyword deriving is used to derive the data type as an instance of a type class. And typically, the standard functions that are supposed to be defined on types of the type class are defined by default. For instance, equality, order, show, etc. Then you can also define data types with parameters, as in the example of shape, person, etc. You have two different types of user-defined data types. One you might call the sum type or union type, where there are multiple constructors on the right. The example here is day or shape. Or the other is the product type or the struct type that you might be familiar from other languages, where you have only one constructor on the right. The example of this is person.